Okay, well, good morning, everyone. Thank you for joining us today. It's an absolute pleasure to introduce Professor Bistra Dilkina. Bistra is a Dr. Allen and Charlotte Ginsburg Professor in Computer Science at the University of Southern California. She's the co-director of the USC Center for AI in Society and also the site lead for AI4OPT at USC. Bistra is one of the world's foremost experts in combining AI and optimization, in particular for machine learning in optimization solvers. She's been pushing this combination for a long time, organizing events like CPIOR, I think CCC workshops, the Bridge program at AAAI recently, so really big advocate here. I think I talked too much already. Without further ado, please help me welcome Bistra.
Hi, everybody. It's a great pleasure to be here and be back at Georgia Tech. I actually started my academic career as an assistant professor here at Georgia Tech in 2013 in the School of Computational Science and Engineering, CSE, in the College of Computing, and was here for 4 years and a half before I went to USC to co-lead the USC Center for AI and Society. And so it's like my first academic home. So I'm really, really glad to be here. So today I want to tell you a little bit about my kind of research agenda. In particular, a lot of my work focuses on creating synergies between machine learning and combinatorial optimization in order to guide the next big step change in our ability to solve real world problems. And in particular, the way that I approach this is twofold. One is trying to inject machine learning in combinatorial optimization solvers, and the other one is trying to bring in combinatorial reasoning and constraint inside machine learning pipelines. So, for example, in fusing discrete optimization with machine learning, I started my foray in this actually here at Georgia Tech in 2017, where we kind of proposed a first big success on ML-guided combinatorial solving, looking at graph optimization problems and essentially learning novel greedy heuristics for those graph optimization problems using RL. So this was this kind of started this whole then paradigm that I've been focusing on. And in particular, most of my work has actually focused on combinatorial problems, hard combinatorial problems that can be modeled as mixed integer programming, and looking at today's solvers, both complete and incomplete, and the many kind of engineered heuristic components that they have, and how we can introduce ML components that can guide them in order to achieve better performance. And I'll share today a lot of these successes here. But then we've actually taken this kind of paradigm and brought it to other combinatorial domains. For example, multi-agent planning, which are AI planning problems that are also NP-hard, which have their own kind of search heuristics, tree search, and so on. And there we've shown similarly huge successes by bringing this like kind of paradigm of ML-infused, ML-guided combinatorial solvers. The other direction is more about thinking the setting where we build predicting models which are essentially estimating parameters of an optimization problem. They're estimating prices or demand or supply, basically the cost coefficient, the objective coefficients or the right-hand sides of constraints and so on. And so when we know that we are basically training an ML model that will really be driving a combinatorial optimization problem down the line, how can we think about exploiting that knowledge? And so we propose this framework of decision-focused learning, where we are saying, well, we want the ML model not just to be accurate at mimicking historical data, those prices and demands, but once we take these predictions and we plug them as coefficients in our optimization models, get the solutions from those optimization formulations, and then plug them back into the real world, where the parameters might be different than what we estimated, how good are those solutions? So that's what we term the decision quality of the ML model, and integrating those reasoning about these combinatorial problems as differentiable layers in the ML training. So this has resulted in a line of work that focuses on combinatorial problems that can be modeled as submodular optimization, as linear programming, as graph optimization, facility location problems, or even just as generic mixed integer programs. And then we have used those models in some impactful applications in public health and biodiversity conservation. And then we've extended this idea back to solvers and basically using these ideas of differentiable optimization to design novel and scalable differentiable optimization solvers for mixed integer nonlinear programming. But today, I really focus on one piece of my research agenda, which is our work on ML-guided mixed integer programming solving. So as you all know, this ISW department, MIP is a very powerful mathematical framework that models many real-world problems with linear constraints and linear objectives and discrete and continuous variables, but actually can be broadly applicable to all sorts of scheduling, network design problems, operational problems from airlines, from energy, from supply chains, from data centers, etc. So therefore, improving the state of the art in solving mixed integer programs, especially for the kind of large-scale real-world problems that clients and industries might be interested in, is extremely important. And talking about clients and industries and real-world problems, one thing that is a very, very common setting is that usually a specific organization, let's say UPS, has really a combinatorial problem that is not a one-shot problem. They have to solve different versions, different variants of the same problem over and over again. Every day, they have to decide how to dispatch and route their trucks to deliver the packages that are needed for this day, right? So it's the same kind of a routing problem, but with different data, with different coefficients every day. So this is what I call the distributional setting, where we are going to be solving a family of mixed integer programs that come from a distribution, but the underlying problem structure is very similar, right? The constraints are not fixed, the objectives are not fixed, the parameters might change, but the problem kind of is the same. So if we're in this paradigm, can we do better than just thinking about a MIP solver, a solver that can solve any MIP, like Gurobi or Cplex or Express, etc. So once basically you think about ML-guided combinatorial search, you can think about the fact that this ML guidance can be specialized to that particular distribution, and that's where the power of this idea comes. We're going to create kind of dynamically learn specific strategies that work very well for that family of problems, and then might not work well as a generic solver. So we're hoping that by treating this problem as historical instances of the optimization problems, essentially become a sample of an ML learning problem. We're hoping that we're going to get better performance than a generic one-fits-all solvers. And also, it will reduce the need of hand designing heuristics, which essentially what happens in practice. Like maybe there's an OR team at UPS designing like heuristics that would work better for their particular problems. Instead, we just ask them to collect historic data and train through machine learning our specialized solvers. So there's a rich landscape of literature. When we started, there was basically almost nobody doing this, and now there's like an explosion of very interesting results that are trying all different directions of how this can be approached. The kind of historically first foray in this was actually much earlier in 2010, maybe even before that, more in terms of using machine learning for hyperparameter configuration of combinatorial solvers with SMAC and HydraMIP, but now we are really exploiting into how to inject machine learning into actual algorithmic frameworks like branch and bound for MIP, where we can think of all the components that don't compromise the optimality guarantees of branch and bound, and yet have a big impact on how long it takes to get good solutions or get good bounds. So things like selecting which variables to branch on, which nodes in the search tree to prioritize, which primal heuristics to run at each node, which cuts to include, etc. All of those are essentially incredibly important components that are right now guided by, engineered hand-designed heuristics. And there's been successes, including in my group in Bolt, in all of these aspects. But beyond going branch and bound, and today I'll also show you some of these advancements, we've also looked at incomplete methods for very large scale, very difficult mixed integer programs, again, with this ML-guided component. And obviously this goes beyond MIP, and there's a lot of work in SAT, in VRP, TSP, pseudo-Boolean optimization, constraint programming, etc. Okay, so today I will show you a few examples of how this works and what kind of improvements we can get. I will start with large neighborhood search for mixed integer programs and introducing this idea of contrastive loss in order to guide our training of the ML-guided components. And then from that success, bringing this contrastive loss as a unifying paradigm for ML-guided MIP and showing 2 more places in which we very successfully deployed this kind of modeling for both predicted search and branching priority decisions. And then I'll talk about how do we advance the field in terms of benchmarking and thinking beyond single ML component training. Okay, so what is large neighborhood search? Is an incomplete search method that works very well for very large scale, very hard MIPs where branch and bound is not an option. So where we basically start with an initial solution, which might be very bad, then we unfreeze, destroy part of the variable assignment, we keep everything else fixed, and we re-optimize just those variables and constraints that are unassigned, and then therefore get a new feasible solution that becomes hopefully the incumbent if it's better, and then we choose another set of variables to destroy, and we keep on moving in the space of solutions step by step, hopefully converging to better and better solutions. So this is a paradigm that has been actually deployed successfully in many large-scale real-world applications, both in the world of MIP, but also in specific domains like VRP and TSP and so on. So here, obviously, one of the most important components is how do we decide which part of the solution to destroy that we're going to re-optimize next? If we select badly, then even if we re-optimize them, we basically might not find any assignment to those unfrozen variables that even improves the current incumbent, right? Or we can find one that just slightly moves our objective. So this is a very important thing in terms of how quickly we are stepping down in solution quality. So perfect opportunity for machine learning. So what we want to do is we want to find what are those good candidates. So if you're thinking about learning how to do this well, the first step is how do we get training data? What are we trying to imitate, right? What's a perfect candidate that we might collect offline in order to train our model? And here comes actually an approach that has been proposed in 2003 called local branching, which explicitly models this. How do we find the best optimum subset of K variables such that if I unfreeze them and I re-optimize the problem, I would make the biggest improvement in my objective? In fact, it turns out that you can formulate this in the context of MIP as just the same MIP with just an edit constraint that just says, given the current assignment, if there you can flip zeros to ones and ones to zeros at most K times. So this is basically saying, I don't care which K you choose them such that the new objective after you're allowed to flip those K variables is as good as possible, right? So essentially solving this MIP is going to give us the best possible destroy set. We cannot do this in the context of LNS because then every step of the LNS would involve solving a MIP problem that essentially has the same number of variables and n+1 constraints as the original one. Why we're using LNS to begin with is that problem is very hard and we cannot really solve this. It takes too long. So what we can do is we can use this offline ahead of time on historic instances, investing compute time to do this in order to collect those training sets. Then the idea is that we're going to learn how to imitate them. And then when we get new test instances, we're not going to be running local branching. We are just going to choose our destroy sets with our machine learning model. So offline, big computational investment. This is kind of a running property and a con, but also that's where the advantage comes from. You have to like kind of invest a priori computational time and data collection to achieve this improved solver performance. Okay, so we're going to solve the local branching. So in hindsight from that solve, we know that the variables whose values change would have been the best destroy set. Treat that as our label, right? That we're going to try to learn. And so note that here we are predicting sets. We have to predict a set of variables that we want to destroy, which also has its own difficulties as opposed to like predicting a regression or a classification problem. Okay, So what a lot of so we basically can like kind of look at the solution and then decide which variables you should include in your destroyed set. And so this idea of learning to imitate local branching actually did not come from my group. It was first proposed in 2021 by a group of researchers at DeepMind, which basically showed the promise of this ML-guided LNS idea. And they ran huge experiments with data collection and training using imitation learning, where they would get that optimum solution from every local branching solve, use that as their label, and train models to predict those sets. Okay, so at test time, what they'll do is they'll use the ML model to predict each one, how likely each variable is to be in the best destroy set. And so when we came along, it's like, okay, this is great. This already is improving the state of that a lot. Can we do something different? Can we innovate here? And one of the things that has been kind of like a driving part in the way my group's approach is to really understand this from like an optimization perspective, what's happening. And one key thing here is that there's actually many destroy sets that are equally good, right? So thinking of this as like only a single set is the label that we need to imitate just doesn't hold generally in combinatorial problems. So if we have a lot of sets, we can use multiple sets to imitate. But also the other thing that is very important to realize is that in many problems, what will happen is that there's some variables that are really important. So even if you have a destroy set that looks almost ideal, you have forgotten to include a few key variables. And that means then that move is still not going to be good. So sometimes you might have sets that look very similar to the very good ones and yet are bad. So how can we exploit that knowledge? So here comes contrastive learning. Contrastive learning is a paradigm that has been successfully used in text and image prediction, where the idea is that you actually get a much stronger signal in training your models, not only by providing the labels, like the ideal prediction, but actually thinking about positive and negative examples. So you might say, okay, I have an image and I want to pair it with something that has the same class that looks very similar to it. And I also want to pair it during my training with another image that also looks similar, but it has bad label, right? So this would correspond in our case to the idea of like, I have a destroy set, which is very similar to a good destroy set, but it could be also very similar to a bad destroy set. And I want to exploit both of that information. I want to train my model to predict things that are similar to the positive examples and as far away as the negative examples as possible. Okay, and some of these contrastive learning ideas have actually slowly emerged also in the combinatorial community, with some ideas being proposed in SAT. Okay, so what does this mean here for us? The key thing in using contrastive learning as a training paradigm is to really define what positive and negative means for the task at hand. Again, remember here what we're doing is we're predicting sets of variables, okay? So then our positive and negative samples should also be sets. And so what we're going to do is we're going to get a MIP, we're going to find an initial solution, which is going to be a vector of assignments. We're going to solve our local branching ILP to collect the data. And from that run, we want to get these positive and negative samples, right? So positive samples will become the near optimum solutions to the local branching problem. So destroy sets that are almost give us the best possible improvement of the solution. And our negative examples will actually have to fulfill this desiderata where we want them to result in a bad move, but then we also want them to be similar to the positive examples so that our model learns to discriminate which are the key things that it needs to predict. So what we're going to do here, I'll explain in a second, is to actually generate those in this way. So we get one of the positive examples of our destroy set. We move our LNS to the next solution. We come back. Now we have a new incumbent. We do the same. We collect more data. So we collect this data over multiple steps of the LNS for each instance, right? And we do that over a whole distribution of historical instances. We add this into a training set. we train a machine learning model with contrastive loss to imitate and to discriminate those instances. Okay? Yeah.
Sorry, one quick question. So for the negative sample, you solve the optimization of
I
the
will.
connection?
Next slide.
Oh,
Give me a second. Right. So what is this? Let's dig into what are these positive and negative examples, right? So when I'm solving my local branching problem, which is itself a MIP on which I'm running branch and bound, I'm getting the trace of my branch and bound search. In particular, I get the sequence of solutions. So I can keep, like at some point I stop, I run out of time that I want to run my local branching. I can return the positive, the best solution found, as well as the last few suboptimum solutions as my positive examples. In particular, the way that we implement this is looking at the best solution found while solving the ILP, and then accepting all near optimum solutions within some threshold up to 10 of them, right? So we don't want too many, and we want the best 10 essentially. Now, the more interesting thing is the negative part, right? So again, what we want to do is we actually want to generate destroy sets that are, I mean, it's easy to get very bad solutions from this trace, the initial ones, but those very bad solutions that in the beginning of the branch and bound we're finding could be very different from the optimal solutions. So treating those as negative examples is very weak because they're not anywhere near those. We would never choose them, even if we were just doing imitation learning on the optimal ones. What we really want to tease out is what's the most important part in those good sets that we need to imitate. So to do that, we take those very good destroy sets, we perturb them randomly by just changing a small number of which variables are in the destroy set. Then we resolve basically the local move. How much would that destroy set actually improve the objective? And we look whether it's a bad example. It's a bad example if the improvement is very small compared to the best possible move we could have made there. And we accept that as a negative example if it passes. We keep on sampling until we get, again, around 10 negative examples for each positive example, right? And, you know, changing just 5% might be too little perturbation. Maybe there is no destroy set which is bad that is so close to the good one. So we keep increasing the perturbation. And in the worst case, obviously the perturbation will have to be very bad. That's not what we observe in practice. Yes.
Can you do this solving another limit? Finding the bad examples, your current set, and you're only allowed to change a few things and flip the objective you want to make. Right. Does that work?
You could, and in fact, in later work, we actually designed this kind of like a novel minimax problem, which essentially is explicitly looking for those bad examples. Here in our first attempt at this, we found this solution, and we didn't think of doing it more explicitly. So as I said, the contrastive loss, essentially what it does is it has a destroy set in our positive label. It has the predicted label, the predicted destroy set from our model pi of x, where x are the features of the particular MIP and incumbent solution we are at. We want our chosen predicted destroy set to be as close as possible to our positive example of a destroy set and as far as possible from all the negative examples of the destroy set, right? So we are kind of trying to make a discriminative loss where we are pushing those close, pushing the other ones apart. Yeah.
How do we expect the difference to be between the elements of the positive sample and the negative sample? So what kind of a difference are we looking at over here?
So again, so because these are sets, so essentially a binary vector of 0, 1s is the variable in the set or not, right? And so some of those are going to be in both, some of them are going to be different, and the difference is not going to be too large because of the way we sample our negative examples, where we're looking at 5 to 10 to 20% perturbation, right? So these are going to be binary vectors that are not going to be very different from each other.
And this is a set of some sampled solutions, some sampled feasible solutions.
Yes. Sampled sets, sampled possible set destroy sets. So one thing that's very important to understand is A is not a solution to the MIP. The 0 and the 1, the interpretation is 1 means include it in the destroy set, 0 means keep that variable fixed on whatever value it is. It's not saying anything about the value of the variable in the solution. It's saying about the choice to include it in the destroy set or not, right? It's modeling the destroy set choice. Okay, and so what is this model that we're training? it's a neural network model where we start by representing the mixed integer program as a bipartite graph, which actually has become kind of the go-to model in ML-guided MIP solving, where we have all the variables represented as nodes, the constraints represented as other set of nodes, and then edges between the variables that appear with a non-zero coefficient in each constraint, and then the objective coefficients as a feature, the right-hand side as a feature to the constraint nodes, and the A matrix as features of the edges between them. And in addition, there's a bunch of other features that we include for each of those nodes in the graph based on the rich MIP literature that has guided decisions about MIP solving and about LNS, things about like how tight the constraints are, how many of them are, the degree, the tightness, the solved with basically tight constraints, etc. And in addition to that, these are a lot of features that are only depend on the MIP, the original MIP, right? But now if you think about it in LNS, what we're doing is we're choosing a destroy set at every step of the LNS. If all my features were just MIP features, I should be choosing the same destroy set every single step. There has to be some dynamic features that basically represent the fact that I'm in a particular incumbent and I want to choose a destroy set that's relevant to that incumbent solution that will improve that incumbent solution as much as possible. So we also have features that are based on the most recent solutions in the LNS state exploration. So that's why our destroyed set predictions change from step to step. Okay, and so with this graph representation of the MIP, we essentially run a graph neural network, message passing on it. Well, it's in this case a graph attention network where we basically combine the variable features and the edge features through some transformation layers in order to obtain a final feature vector for each variable. We run this through a sigmoid, which essentially is a 0-1 prediction of whether that variable should be in the destroy set or not. And then we run this prediction of 0-1 into our contrastive loss, right? Where again, we are trying to compare to positive examples and to negative examples, feed this loss back, improve the coefficients, parameters of our neural network model. So all of this is done offline. We train this model to minimize our contrastive loss. At test time, we are just using this model where we get a MIP, we compute the MIP features, we find an initial solution, and we compute the dynamic features. We run this through our neural network. It gives us what destroy set to choose. It has basically these 0-1, soft 0-1 predictions of how much it likes each variable to be in the destroy set. We greedily choose the top K to destroy. We re-optimize, as LNS always does, get the new incumbent, run the model again, and do that again and again. So instead of having some kind of heuristic, which is usually what lives here, we now have a neural network. Okay? Yeah.
The offline training is on that family of MIPS?
Yes, that's what I started with, the distribution. You have a family of MIPS, which come from a specific distribution, right, which your client has, where the expectation is that your test instances, after you deploy this, will come from that distribution as well.
To have the same size, same number of variables?
No, very important question, which I forgot to to emphasize. What is really nice about this graph attention network is that this size and permutation invariant. Because we are modeling the MIP as a graph, these parameters of the model work on, for each node in the graph, how I'm going to combine the information from my neighbors in the graph, from the constraints to the variable and from the variable to constraints, which means if I have a MIP that has more nodes, I already have the parameters. If I have a MIP that I switch the columns and the rows, it will still work exactly the same, right? So it's invariant to permutations and invariant to size, which is very important because in most places, in most real world scenarios, you're not going to have a fixed size MIP. So that's extremely important. Okay, so I'm going to show results on two benchmarks, which we evaluated on. In our paper, we have results on two more. So we are looking at vertex cover, minimum vertex cover, where we can, again, generate a lot of instances from a particular graph family. In this case, we are looking at Barabasi random graphs, and combinatorial auctions, which is a problem where we have items and bits, and we are trying to basically decide on bundles. And again, there's very nice established kind of generators that can produce these distributions of combinatorial auctions that we can then train and test on. And again, notice that these problems are quite large. They have thousands of variables, thousands of constraints. If you're going to be using LNS for a problem, that problem should be hard enough so that branch and bound cannot solve it like in half an hour, right? Or so these are hard, large problems. And so, and in fact, what we call these problems are the small problems, although they're not small, they're already hard, but I'm going to show results on even larger problems. Okay. In particular, we're going to train our model on the small ones because the data collection is so expensive. We're going to show how we work in distribution on the small ones. Then we're going to also test that model as is on larger instances within the same problem domain. So what we're going to compare is to just using branch and bound, using random LNS, which surprisingly is actually a very common practice in the industry. And we actually in our preliminary experiments found that it works surprisingly well, much better than a lot of heuristics. We'll compare to LB-RELAX, which is actually a heuristic that we proposed before this work, as we were starting to work on the ML-guided work, and we were trying to figure out ways to generate good data. We actually kind of came up with a heuristic that works very well, that's not ML-based. And then the two prior work, imitation learning and reinforcement learning. So the big paradigms in learning that so far has really been popular in using for those problems. We are benchmarking against them, and our method is called CL-LNS for contrastive loss LNS. Okay, so here you can see the performance in vertex cover and combinatorial auction. Our method is in magenta, and you can see that it significantly outperforms all of the baselines, in particular the second best in both cases in imitation learning, and yet there's a huge gap in terms of how quickly we converge. We close the primal gap with the contrastive loss versus just the pure imitation loss. Okay, yeah.
So the branch and bound is the IP that you solve with the cardinality constraint. Right?
No, that's not the local branching, which is the one that's looking for a destroy set, is a different one. This is just treating the original MIP. Yeah, it's like, oh, I'm not going to use LNS. I'm going to use just branch and bound. It's just to show you that these problems are hard. If I was not using LNS, I would get extremely bad performance, right? Gray. The gray is branch and bound, this one. So it basically stagnates really quickly at a larger gap than what you get with LNS. So again, because otherwise I could be using LNS when I don't need to. I mean, obviously it's much easier to just use branch and bound. For our benchmarks, we the first thing we did is like, is this hard enough for branch and bound to even motivate the LNS work? And it clearly is. And so this is basically the explicit behavior over time. And then if you think about the area under the curve, which is the primal integral, which in a sense captures the anytime performance of the solver, how quickly are converging to good solutions. Here is the primal integrals for those same plots that I just showed you. And you can see that again, clearly that the contrastive loss has significant improvements over the prior work. And in particular, reinforcement learning is not working very well. So, okay, that's great. This is in distribution. We learn over this distribution, this specific problem domain, for a specific kind of like size. Now, what happens if like my problem grows? So when I double the size, so this is not like a small generalization, this is like quite large generalization to double size problems, we see that again, those ML trained problems, actually all of the ML baselines are providing quite good, well, actually, again, the RL is not necessarily doing very well, but our model actually generalizes extremely well and still outperforms all the other benchmarks. And here, I guess the point I wanted to make is that this heuristic that we came up with, LB-RELAX, is actually working very competitively to the other ML-guided baselines, except our model is the only one that can bring something new to the table. So this was extremely encouraging and very promising. So we basically showed that we have 26 to 69 better rate of improvement, which is the primal integral, over 4 different domains, beating not only heuristic baselines, but also very strong machine learning baselines using machine learning and imitation learning and reinforcement learning, and extremely strong generalization performance. So from here, we were like, okay, so there's really something in this contrastive loss, this idea about the fact that we want, we want to be thinking about how we create discriminative models which are able to distinguish between good and bad choices, not just give them good choices to learn from. And so we basically thought of this as kind of like a framework that we can apply to many other tasks in MIP solving. So we want to identify a decision to improve in the search algorithm. We want to think about, for that particular component, like the destroy set in LNS, what does it mean to be positive or negative examples and how we can create them? That's actually where the bulk of the work goes, thinking about that process. Then we need to figure out a procedure that will allow us to collect these positive and negative examples, and then train with contrastive loss in order to improve the performance. Okay? So, and then test the test performance of this whole thing. So I will show you two more successful examples of this framework. One is called predict and search, which is also an incomplete method like LNS. But essentially here, what we're doing is instead of having this iterative unfreezing of variables, in many problems, you might not be able to find a feasible solution to start from the LNS, right? So predict and search is very good for problems where feasibility might also be hard. But the idea is that the problem is so hard and so huge that if you just run branch and bound, you might wait for a long time to get any kind of improvement of the primal bound. So here is, you're going to select a set of variables and you kind of prefix them to either 0 or 1. You have to decide how, through some heuristic. And you're essentially, in a heuristic way, shrinking your MIP, and then you do branch and bound and the rest. Obviously, if this is not good assignment, you're solving given the subproblem to optimality, you don't have any more guarantees, any formal guarantees in terms of the optimality with respect to the original MIP, but it might still be a good way to find good solutions quickly, okay? And one thing that people have done to improve, to curb away mistakes in this partial assignment is to say, when I run the branch and bound, I'm not just going to freeze this assignment. I'm going to allow my search to actually change up to delta of those assignments. So it's creating kind of like a trust region around this assumption that you know what you need to do for some of the variables, and say, actually, I want you to assign them, but I'll give you some freedom to choose something else. And this works way better because when we don't have, when we make mistakes in these partial predictions, okay? And so in fact, in 2023, there was a really nice paper at ICLR, which said, okay, this paradigms is great. How do we do this with machine learning, where we, again, train a model to decide which those partial assignments of 0, 1s are, and then we put this into the predict and search framework. So they proposed essentially an imitation learning paradigm again, where they collected data of optimum solutions for the different MIPS or near optimum solutions, and then train a model to imitate those optimum assignments as good as possible using cross entropy loss, right? So this is kind of the imitation loss of just good examples. So we're like, oh, well, again, you may know that you might have, solutions that look very similar to each other, and yet one has extremely bad quality and the other one doesn't. So can we actually introduce this idea of contrastive loss? So use contrastive loss instead of this imitation learning loss here. So so that's exactly what we did here. Again, thinking about how are we going to define positive and negative examples. The positive examples are, again, easy. You offline, when you're collecting data, you're running your branch and bound solver, you're recording the best solutions that you found, and maybe the best last few solutions that you found. Now, the negative examples are a little hard. And one big problem here is that with these partial assignments, you could actually even generate infeasible problems, right? If your partial assignment is very bad, you actually might not even have a solution to the subproblem. So negative examples, there were two types of negative examples we thought of, partial assignments that look very similar to the positive examples and result in an infeasible subproblem, and partial assignments that look, again, very similar to positive examples, but actually result in very bad solution quality from what you can find in the subproblem that you defined. So again, the key part is deciding how to actually navigate this positive and negative example definition. And so For infeasible solutions, we basically, again, we did the random perturbation where we take the partial assignments that we have found through branch and bound search. We perturb a small set of those assignments, resolve the sub-problem, see whether it's infeasible. If yes, it becomes a negative sample. If not, we keep on sampling. For the low quality solutions, we actually define this novel minimax optimization problem where we are trying to find an assignment that is not too far away from the optimum, from the positive partial assignment, and yet the objective is as low as possible, right? So again, the key thing is similar but bad, okay? And so how does this work? Again, we're trying to compare to two very strong baselines that are already using machine learning, neurodiving, which also came from Google, and this predict and search with GNN from the ICLR 2023 paper. And we showed, and both of them are in a sense in a spirit imitation learning based approaches. And we showed that the two versions where our negative examples are based on infeasibility versus negative examples based on low quality, both of them work very well, where the infeasibility negative sampling actually seems to work better than the low quality negative sampling seems to give us a better advantage than the infeasible. Obviously, that would depend on the particular benchmarks. For those 4 benchmarks, it seemed like the low quality ones is better. Okay, so again, here we test this generalization to larger instances. And again, we show that we have huge savings, 58 to 70% lower primal integrals compared to the best next baseline for any of the benchmarks, right? And again, these are problems where just vanilla branch and bound would have worked quite badly, right? So these are really hard, large-scale problems. Okay, I'm talking really fast, but oh, I'm doing well. No, I'm not doing well. To show you another example of this is in backdoors. Backdoors is a concept that there's for a lot of real-world problems, you have a set of key variables such that if you actually make choices about these variables, the constraints essentially propagate and push the other variables to take certain values, right? So it might be like you're doing a configuration, you might have to take key components of the design, and then the rest somehow is implied through constraints. And that actually was introduced first in SAT, and shown that in real world instances, those small backdoors exist. And then in my PhD work, actually, I generalized this concept to mixed integer programs and showed that a lot of real world domains also have that. So now our goal would be to use this concept of backdoors to guide branching. So I'm going to try to collect offline examples of these backdoor sets for historical instances, and then I'm going to train a model to try to guess them. And then once I've guessed a backdoor set of variables, I'm going to give that as a branching priority to the solver, to Cplex or Gurobi or whatever, saying first branch on those variables at the top of the tree, then go to anything else, right? With the idea is that if I branch on those backdoor variables, my search tree will be way smaller than if I don't, if I leave it for later, deeper in the tree. Okay. And again, backdoors have been shown to exist in many domains and as well as in MIP. And there's been quite a bit of prior work. And in fact, my group started with this backdoor idea earlier in 2022, before we came with the whole contrastive learning, and we came up with a kind of imitation learning sample. Actually, it's not imitation learning, but sample and rank approach, which had modest success, right? It was a lot of work and we were having a really hard time to make the model learn how to predict this. So now we were like, okay, we have this new tool, this contrastive loss. Let's see whether we can actually do better than whatever else we had tried. So, so again, what we're going to do here, we're going to take a MIP. We're going to run it through some model that we're going to pre-train. That model will guess or predict what variables are in the backdoor. And for those variables that we guess to be in the backdoor, we're going to set the branching priority to top 0, and then everything else will be branched on later, right? So this is like an upfront thing that you do once, and then you run your solver. So one thing I want to emphasize that's really nice in all these 3 examples that I've shown you so far, we need only black box access to the solver. We don't need to be able to have API and go in, like this could be Skip, it could be Cplex, it could be Groby. This works for any, on top of any solver. Okay, so here again, we are using the same architecture with the graph attention work and the bipartite graph. And we just have to think about how do we implement this part and how do we collect backdoors? How do we determine what positive and negative means? Okay. And the way that we collect backdoors, which was also very important, leveraged also an earlier work of mine in collaboration with University of Toronto, which basically designed a Monte Carlo research method that searched for these backdoors. So finding the smallest backdoor for a combinatorial problem like mixed integer is sigma 2 complete. So it's actually harder than solving the MIP itself. So we need, the data collection is very difficult. And so we need smart ways of doing it. And we luckily had already worked on designing this. Obviously, this is not something you can use for solving. It was more like, do problems actually have these small backdoors? How do we find them? And so on. But in our case, it was useful because it could be used for training data collection, although it's not useful for speeding solving in practice. Okay. And so during this Monte Carlo research, which is basically based on a reward based on estimated tree weight, how large is the expected search tree under a particular backdoor, we can select the top K backdoors from which the Monte Carlo research has encountered based on this estimated tree weight, which is a surrogate for how large the search tree is. And once we've chosen those top K candidates, we can actually solve the MIP with those branching priorities and really see what is the real runtime, because the Monte Carlo research doesn't have actual runtime. It's using a reward based on estimated tree sizes. So now that I have this like 50 case, let's say 50 backdoors, for each one, I know exactly how long it's going to take if I were to set that branching priority. I set the ones that are the fastest as my positive examples, and the ones that are the longest as my negative examples. So in this case, we didn't have a very sophisticated way to do this. The only thing that I can say is that these ones were anyway already similar to each other because of the way that Monte Carlo research explores. It actually does perturbations, which means that the last best K candidates are already kind of similar in spirit to each other. And so one thing, so here again, I want to show the improvement over Gurobi. So Gurobi obviously is a state-of-the-art solver. It's really hard to beat Gurobi on branch and bound. And so here in the red, you see the improvement over Gurobi, where 0 is we match Gurobi performance. Above is like we are speeding it up, and negative means we are slower than Gurobi, right? So in this case, I'm reporting runtime because actually these problems are kind of easier because actually finding backdoors is very hard. So we could only do it for smaller scale problems. And so you can see that with the contrastive learning, we actually have on average around 15% improvement over Gurobi, which is a big feat for us, given how well that solver works, especially on medium difficulty problem. And our previous approach is not nearly as robust, which we already knew. It was kind of hit and miss. And the other interesting thing to observe is that we actually, when we see which problems are we speeding stuff on, if you plot the runtime of Gurobi on an instance versus the speed up on that specific instance from contrastive learning, you can see that these 15% speed ups are actually mostly on problems that Gurobi is very slow at. So not only that on average we have speed ups, but we actually have speed ups on the hardest instances, okay, which is even nicer result. Okay, so under this contrastive loss framework, I've shown 3 successful examples, and I'm sure there's many more to explore. Right, so I'm really convinced, I'm like a huge convert about this idea about thinking about discriminative training, especially because the kind of tasks that we encounter in ML-guided solving is not just your generic ML. Most of the time, we actually have to, we are doing a structured prediction. We are predicting a set of variables to branch on. We are predicting a set of variables to destroy, right? We are predicting a partial assignment, which is not, I'm not predicting individual values. It matters how the whole thing works together, right? Which is a specific type of ML prediction, which I think it really benefits from what contrastive loss brings to the table. So in order to drive this, this community forward, one of the big challenges is benchmark and data sets. And you'll see, as I said, there's many papers, many people working in this space. And unfortunately, so far, everybody has been like generating their own data, reporting results on similar problems, but like changing, let's say, the graph distributions for the vertex cover, etc. So we haven't been very good at like benchmarking the way that the SAT community has done it, which has, I think, really helped them grow their like methodological trust. So we identified this gap. And so basically, my group was like, okay, most of the work is either using heterogeneous instances like MIPLIB, which is just not really fit the whole distributional argument, or they're using same domains, but with different parameters. And also most of the domains are literally synthetic, including my own group is guilty of the same. Combinatorial auctions is a real world inspired problem, but is a synthetic generator. Vertex cover, same. Okay, so we basically developed this distributional MIPLIB, which is a multi-domain library for advancing ML-guided MILP. And we basically combine synthetic benchmarks that have been used across all of the literature so far, and we standardize them. We created definitions of what easy, medium, and very hard means. We pre-packaged train validation and test sets so that people can compare on the same things and actually be able to claim that they win over another problem. And we included problems from, you know, graph optimization, generalized independence set, capacitated facility location. So both binary as well as mixed integer problems, and standardize them and document them. What's even more exciting is that we also created a set of real world benchmarks. In prior work, we had already made some progress by using maritime inventory routing problem library and instances that come from real neural network verification problems that can also be encoded as MIPS, where you're looking for adversarial examples. But we also worked with actually friends here at Georgia Tech to get real benchmarks from energy, transmission switching from Dan's group, and supply chain consolidation network problems from Alan's group. And my group contributed a real-world benchmark where we work with LA Department of Water and Power, working on their water infrastructure and looking at hardening network design problems there. And so what does this open? So we started thinking about what's the other key challenge is data needs. This pre-training data collection is extremely expensive. And so creating this library also allowed us to kind of think about this question as well, where we said, okay, what happens when we have very little historical data? Can we pool data across domains and train models that maybe work well with this pooled data? Obviously, that kind of breaks the whole distributional argument where I'm trying to do something specialized for a benchmark. But if you have no choice because you have little data, you might still have an advantage. And that's exactly what we showed here, is that when you have very little training instances per domain, you actually get better mileage from an ML model trained across data from, say, 5 different domains versus a model trained on a single domain. Okay? So models trained with pooled data exhibit better performance when limited training data is done. Here we looked at 80 training per domain, 80 training instances. That's obviously a very big restriction. So I said, okay, what happens if it's not that bad? Let's say we have like 300 plus instances. At this point, the advantage of mixing, pooling actually disappears. It matches, it doesn't get worse, but it matches the performance. But the interesting thing is that when we try to test those models on generalization, where we're trying to like double the size again in the instances, we find that the models that are trained on a specific domain actually generalize worse than models that were trained on mixed distribution. And again, because the model is seeing instances from different sizes, from different structure, is able to I think, a better handle the fact that the larger instances obviously have slightly different problems. So this mixing distributions is helpful in both data scarcity as well as in generalization. So now we've shown this, this idea of multi-domain pooling. The other natural idea is multitask pooling. By task here, I mean not a domain, but the algorithmic task, right? I've shown you training an ML model for backdoors, training an ML model for LNS, training a training model for predict and search. All of these things were done individually and trained from scratch. But if I want to have a portfolio of solvers for a particular domain, my company has some kind of a vertex cover facility location problem, but I want to have a portfolio of solvers, and this portfolio might all be ML-guided LNS, ML-guided paths. Why should I be doing this separately, right? So can we actually leverage combined training across these tasks in order to learn a model that provides some kind of useful mixed integer embeddings that then can be specialized for different algorithmic tasks? Obviously, multitask training has had huge successes in other domains, from vision, from language models, etc. So it's a very natural extension to be thinking about. Okay, and so what we're going to do here is we're going to have multiple tasks with collected offline data, train a model where we are combining the losses from these multiple tasks to decide what the neural network parameters will be. And in this case, we are keeping the task layers fixed, but we are optimizing the embedding. And then once we are done, when we want to test, we are actually going to take a specific algorithmic task, fine-tune just the task layer to do well, but fixing those embeddings as a kind of like a common model, and then see whether we do better. Okay. So again, what we're going to do here is we're going to leverage our existing architecture, but this framework, in a sense, we really position this as a framework where this network architecture could be something different. We're actually already working on thinking, can we throw away this GAT and do something smarter, right? And you can still plug this in here. You know, what the task layers are, again, you have to think about what is this multitask learning. In our case, for now, we only had 3 tasks: backdoor prediction, predict and search, and configuration. Configuration is basically choosing the parameters of skip, which also has dramatic impact across different instances. And then what we're going to do is we're going to train this multitask model for 2 tasks and then test it on those 2 tasks or on a new task, the 3rd task. So we're doing backdoor, predict, and search, and configuration. And in our case, we're using contrastive loss for all 3. But again, the framework is set up in a way that these losses can be, one of them can be regression, another can be cross entropy, another can be contrastive loss. It doesn't matter as long as you're properly getting gradients from all of them. So here is what we obtain by training on backdoors and predict and search, and then fine-tuning on backdoors. So this is in distribution. The backdoor algorithmic task was already in my pre-trained instances, but I'm fine-tuning it, fine-tuning the task layer to do very well on this. And so you can see here that we are doing better than a single task model, pre-trained from scratch, specialized just for that algorithmic task. And in particular, our advantage increases when we are trying to generate larger sizes. So that's exactly the kind of behavior we want to observe. But the more interesting thing is what happens when I try to actually extrapolate to a new algorithmic task that didn't even participate in the embedding, because that's going to be in the future when people come up with more use cases for ML-guided MIP solving. They're going to come up with stuff we've never seen before. Can we speed that process by having this pre-trained multitask model? So here are the results of what happens when you train on 2 tasks and test on the last one. So pre-trained on backdoors and configuration, but tested on predict and search. This is pre-trained on backdoors and predict and search, but tested on configuration. This is pre-trained on predict and search and configuration, but tested on backdoor, right? So take 2, leave 1 out. And again, what we observe is that multitask model generalizes to completely new tasks very well across all 3 possible setups that we have. And additionally, here we are also testing on larger instances than what we trained on. So it's even a bigger ask, is asking to generalize both to a new task and to larger instances. So this is extremely promising. And so we basically shown this superior performance, and really we see this as our first step towards a foundational model for machine learning guided MIP solving, right? So we've shown the benefit of multi-domain training, multitask training. Our next step is to actually put this together, expand vastly the tasks as well as the domains which we have to train on, and really try to push forward a consolidated model that can use as a warm start for all sorts of things down the line. So with this, I want to just re-emphasize that this synergy of machine learning and discrete optimization is extremely exciting. There's so many ways in which one can approach it. I just showed you one particular way in the context of mixed integer programming, but this community is growing, and I'm think that a lot of exciting new stuff is going to come out in the next 5 to 10 years. So thank you so much. And I'm happy to take questions, although I don't know.
Yes, we're all thinking how much computing time you spend in trading.
Yeah, there's a lot of compute time in the data collection, right? So the training is actually not the big overhead. And that's one thing that people don't understand when you're doing ML guided for combinatorial. It's like really solving those MIPS. Each sample is like 1 hour of compute. So it is quite a bit of training. Yes.
So in total, how many hours, days? I mean, just to give us a sense.
So if you think about, like, let's say we have 900 train instances. For each one, we are collecting at least 100 to 200 different things, like different backdoors or something. And each one of them is 1 hour. So how much is that?
100,000?
Like 10,000, 10,000 hours, 20, more than that, but a lot. That's for each one separate paper. So when you combine it, it's huge. Yes, it's a little it is a big overhead. I mean, but I think if you think about like how, let's say, Gurabi or Cplex are like trying to fine tune their solvers to like present their newest, like they most likely under the hood are doing a lot of things like this. Yeah. And ideally, my vision is that if, let's say, I have a company that's trying to use this, right? They're going to use this just for their domain, right? And maybe one particular search methodology. So it might not be as big overhead. But it's an important dimension. Any other questions? Yeah.
Building a bit on what Dr. asked, in most of the experiments that you shared, I think the number of data points that you had was in the order of a few hundreds or a few thousands. And that seems smaller than what we can read in the ML literature of these the billion tokens to train a large language model, or hundreds of thousands of images to train image recognition model.
Mm-hmm.
Can you comment a little bit on like the amount of data that you see in your work versus the amount of data that we typically see in like the flagship ML applications?
Yeah, so I think if we're really pursuing this like kind of big scale training, what we'll do is we'll end up focusing on training data from easier instance. In our case, like so far, we really went straight for the very hard problems. But the idea is that you might want to actually pre-train on easy problems where you can collect millions of small MIP data. That will be extremely fast. Then the question is like you have to see enough diversity to hopefully have something that would then generalize to the larger problems. Or possibly do something like curriculum learning where you start with small and then you use the learned models to hopefully solve faster the slightly larger ones and get more data, etc. But it is possible to get millions of data in this. You just have to be willing to work with easier problems and easier tasks, right? So that's also one thing that we're thinking of right now. How can one run of data collection be actually kind of leveraged as like multiple samples? Like it could be the same run can be used to create samples for labels for backdoor and predictors, like all sorts of tasks. So then you're like kind of, maybe it's like 100 labels from a single whatever, one hour run. So that's where like actually understanding well the optimization literature is going to be critical in understanding how this can be done here. Yeah.
Have you looked at any formulations that don't involve the bipartite graph, like only on the variables? To me, it seems that like the MLP is only a positive variable embeddings at the end, and constraint embeddings, they're just, you don't do anything with them.
We haven't, but I mean, although they're not just at the end, they hold important information, right? So that's why the message passing between the variables to constraints back to the variables. And the thing is that basically a priori, we don't have a good idea of how to embed those features, right? Essentially, the model is learning how does the constraint features play a role for the variables. Obviously, as I said, like I think there's a lot of interesting things to think about how to like modify that architecture, replace it with other things, how to scale it. So one of the big things that essentially the distributional MIPLIB also really revealed is that a lot of like kind of big wins in the literature, once you actually try them on these real world benchmarks that we have that are much larger, completely fail. And they fail not because they're bad in predicting, but the inference time of the graph neural network becomes so prohibitive that it's too slow. So you can't like for example, the transmission switching, you just can't, the overhead kills it. It's much better to run, let's say, branch and bound. As much as stupid as it might go around exploring the tree, it's still faster than the inference overhead. So with that, like, I think having those large scale benchmarks would really push the community to be thinking about like, okay, if you want to deploy this for very large problems, what do you do next, right? So obvious ideas are things like distillation, where you might like train bigger models, but then you might distill them into smaller models that maybe will work for the larger instances, different architectures, and so on. There's a lot to do, a lot of open avenues of interesting questions. Well, thank you, everybody.